Record. Bueno. And I think I got to start my video, share my screen. These got to be really creepy for whoever watches them. Probably not nearly as creepy as me making them. Okay, so thank you for remembering that for me. I actually really say a sincere thank you, although I may come across as smart aleck, but that's just not so today the topic is control volume analysis. I believe it starts, I know it starts on page 177 of the book. I don't know where it ends because I didn't finish the reference thing. But technically it's that whole chapter, but this first part is that part of the chapter. So we'll look at what control volumes are, and then we'll employ the concept of flux in something called the Reynolds transport theorem, which allows us to translate expressions of system behavior, F equals NA. Tell me the balances on across that kind of stuff, through behavior across substitution and control volume. That's really all this is aimed at. So we will start with what is a control volume? It is simply the equivalent of the free body diagram for fluid mechanics problems. So in your other field of engineering mechanics, you had free body diagrams. And probably the most common one was the mighty particle. And onto that free body diagram, you indicated forces. You draw the particle and you say may the force be with you, and so forth. So an extension of that idea is a control volume. So think of it as a free body over more than infinitesimal space. So here it's shown as in this case a cube. It's Picasso did this during his cubist period. Control volume is simply a defined area in space. It doesn't have to be a cube. In fact, in many instances, it will be anything except that. But since we're staying generic for the time being, that's what it is. So here's our cube. And let's look at some features of it. Someone's gone to trouble to draw a cube and shade the faces that are facing us. So inside the cube, there is a volume that's defined. And if you remember back from your geometry class, in your cubist period, the volume of a cube, if one side is delta x, the second side is delta y, and the third side is delta z, the volume of that cube is, actually this is a parallelepiped, but we'll pretend it's a cube. It's a product of those three lengths, okay? So that's what's inside the cube. And a cube is orientable, which means it has the concept of inside and outside. And if we're to look at a small area on any one of the faces, we can identify that small area, we can associate the normal vector with that area, and we can stipulate that the magnitude of that normal vector is equal to the area, and it's pointing outwards from the cube. So if you're inside the cube and you're looking at that particular dark shaded face, you see an arrow firmly welded to the edge of the cube pointing out, with an arrowhead in front of it, and that is your control volume. And we have the mandatory coordinate system, often by implication, but we're supposed to get in the habit of drawing it. So X is coming towards us, Y is going from left to right, Z is going from down to up, and that corresponds to those dimensional values. So the control volume itself is the basis of what's something called the Reynolds transport theorem, and that's employed to allow us to analyze things in a Eulerian reference frame rather than tracking individual particles or collections of particles, which we call a system. In our engineering mechanics, statics, and dynamics, everything was part of a system, and they didn't necessarily move relative to one another. Here we have a little bit added complication because things are fixing to move. If we wait long enough, it'll come off that paper and hit you in the head. The bounding surface is called a control surface. So let's go back to our picture cube. And so these shaded surfaces here that surface, so each of those faces, and there are 6 of them in my parallelepiped here, that surface is called the control surface. And I don't know why it has that name. The people who did this originally are control freaks. So you have control volumes and control surfaces. So things go into the control volume by crossing the control surface somewhere. And if the control volume is initially completely empty, so it's like that volume that's just outside the International Space Station right now, practically nothing in it. There's a few hydrogen molecules in there, atoms in there, maybe a touch of helium, a little bit of carbon, but basically nothing. Any one of us would have a difficult time breathing there. Our expected lifespan unprotected outside the International Space Station. A couple minutes maybe. And of that couple minutes, the last couple minutes would be somewhat unpleasant until we went unconscious. So we have this cube floating out in the space station. That's supposed to be a creepy mental image on purpose. Put stuff into the cube that has to cross the control surface. So if we took a fistful of, I don't know, yummy green gas air, stuck it in there, it would cross that control surface, and we could associate the change in the amount of breathed gas in the cube with how much had to come in across the surface. And that is a word statement of Reynolds transport theorem. But because that's easy, we'll go ahead and complicate it using arithmetic and calculus, equal signs and vector stuff. And by the end of the day, I should have you thoroughly confused. So if we were to look at that outward pointing area vector, and on that particular parallelepiped, we had 6 faces. We had a back face, a front face, left face, right face, bottom face, and a top face. And those area vectors, if you will have magnitude. In this case, it would be associated with whatever the 2 dimensions of the face are. So for example, the back face is delta y units in the left-right direction and delta z units in the up-down direction. The product of those 2 is an area, and the back face is pointing in the minus x direction. So we would write that area vector as delta y delta z times minus I. And that's where all this jargon is coming from. Front face, same area, but it's pointing in the plus x direction. We can convince ourselves of that by going back and looking at the picture. Here's the front. It is delta y units in one dimension, delta z in the other dimension, and it's coinciding with the plus x direction, hence delta y delta z I. Similarly for the other 4 faces. And these ultimately play an important role in the application of control volume analysis. So the general principle is we want to express some conservation principles in integral form. So the first one we have, I'm just going to list them here. First one you have that you remember from whenever you remember it was conservation of mass. Conservation mass is the change in mass of the expected time of a system is equal to 0. That by implication is a closed system. So your body, the human body system, that's not true because you're an open system. You have at least 1, 2, 3, 4, 5, 6, 7, 9 openings. Some folks have more. And things go, mass goes in and out of that. So we accumulate mass. And there's a whole industry dedicated to putting mass in to make more mass come out. You can see those on YouTube. Wonderful weight loss. And most of those probably show this, so I would enjoy it as entertainment, but don't fall into the rabbit hole. Our second one is conservation of linear momentum, which was m dv dt. What was dv dt in our physics class? It has another name. Begin with letter A. Acceleration. So mass times acceleration is equal to the sum of forces. And that's for translation. There's another related principle, which is mass times the time rate of change in angular velocity is equal to the sum of r cross f. That's the sum of the moments equals r cross f. That's what that's saying. Conservation of energy is, oh, that's not typeset correctly. It should say dE dt, the change in energy with respect to time of a system is equal to the rate of heat flow into the system minus the rate of work done by the system on its surroundings. So back in the days when engineers had to actually take thermodynamics, got any mechanical engineers in here? Probably not. They don't like mechanical engineers to take fluids. Back when you had thermodynamics, you would have to be familiar with that. So, example of a system doing work on its surroundings. Imagine, if you will, a balloon. What color balloon do you want? Sarah, pick a color. A color. You're choosing our balloon color. And then you get back. Then you can get back to the text message. Now, question. People hate it when I do that. You just made my day. I love it. What color does it want? Purple it is. Okay, so we have Sarah's purple balloon. And if we carefully add heat to the balloon so as not to compromise the latex that's made out of it and have it blow up, because when that happens, balloons go pop and it ruins my story. But if we heat the gas inside of it, what does your Pivner brain tell you is going to happen? What's going to happen to the P part of the Pivner? Pressure is probably going to go up. If that happens, then the balloon's going to get bigger and bigger and bigger. Well, it has to push against the atmosphere to make that happen. So it's doing work on its surroundings. That's actually a sensible work. We had sensitive enough instrumentation we can measure that. Similarly, we can measure the heat flow going into it. And at the end of that process, the net increase in energy inside the balloon is this DEVT system. All right, Sarah, you can go back to your phone. Our last is the principle, which simply says that also has a type. Okay, we'll get to fix it today, because I'm going to attempt to do my first example live on the notebook later in class. That would be a good time for you all to pull your phones out and catch up on your social life. The entropy principle is the time rate of change of entropy of the system is greater than or equal to 1 over the temperature times the heat flux into the system. So of those are the 5 main thermodynamic principles that the Reynolds transport theorem is useful for. Of those, for most fluid mechanics situations, certainly at the level of this class, the first four will be somewhat useful. The last one is not useless, but it wouldn't enter into much that we would ever do. If we're worried about entropy and whatever we're designing, we've got a lot bigger problems. So we'll just start with continuity, which is the subject of the chapter that starts on page 177 of the book. And we're simply going to apply the control volume principles to the definition of mass and see what we get out of that. Just a quick reminder, remember that extensive properties are properties that are defined out for an entire system. So for example, if the system is your body, your mass or your weight is your extensive property. If you go ahead and we rip the liver out and you're looking the other way, well, actually kidney, they're worth more. Someone shanks you and then the rest of us hold you down, pull one of those kidneys out. The mass per volume of the kidney represents an intensive property. It's extensive to the kidney, but intensive to you. And you don't want to be running around without just each other's kidneys. That's just not, that's mean. So starting with mass itself, the extensive property that mass has is mass. The mass of unit mass would be mass divided by mass, which equals 1. The mass per unit volume, we had a different name for that. That was rho. Also the density. So in the case of mass, if we write the fundamental relationships of ultimately what's going to lead to the Reynolds transport theorem, we could examine the extensive property. So a body with all kidneys is capital B of the system. B for body. The intensive property would be the mass per kidney multiplied, the mass per mass of kidney multiplied by the differential mass integrated over the entire thing recovers the mass of the system. So if you took the mass per unit cell in your body and added up all the cells that you had that make you get back to total mass. That's kind of variant because of the job. The next step, we could re-express that integral as the integral of the intensive property multiplied by the mass per volume of the thing we're studying. And then the integral of beta rho dV gives us the entire mass of the system. So that's all those expressions are saying. I think in your book and in the other books I've used, they're able to make that, a good author can use almost a page and a half, usually by re-expressing it over and over again until thorough confusion. These are just 3 different ways of stating the same thing. So we had a purple balloon that Sarah chose for us. The other way of expressing purple would be RGB 1, 0, 1, and probably an intensity of about 0.7. That's also purple. Or I don't know what the code for purple is in an ASCII table, but it exists. We could go look that up on the internet. They're all purple. There's just different ways of expressing purpleness. And so here, if we actually look at the rightmost one, remember the mass per unit mass in our case, which is mass, that becomes a 1. Rho is mass per volume. dV is the differential volume, and we're integrating that whole thing with respect to volume. So we're adding up the entire volume. So if we put everything into place, M over M is 1. Rho is M over V. And then 1 over V dV integrating over the volume is going to produce V over V. So what we're going to get left at the end is mass. The exclamation point was added. All right, now we're going to get to Reynolds transport theorem. Are you all, for those of you that care, are you mentally comfortable with that? Because I'm not trying to play tricks on you, at least not yet. I'll make it bigger so you can see. So now we're going to look at a gold cube, and we'll go ahead and look at the words in a minute. So here we have some piece of space. In this case, it was a real authentic cube. And everything inside it is painted gold. So at that moment in time, when that picture was created, we can surround the cube with these dashed lines, and that represents our control volume. Our control volume also, that's the outline of the control surface. How many faces are there? If you can visualize it, 3 dimensions. 6, good. There are indeed 6 faces. Then we've labeled the gold mass with the letter M, the indicate mass, and this is occurring at time t, which is indicated with a little t there. And we have our mandatory coordinate system. Now our control volume, that dashed cube in the drawing, that's going to stay put. We're going to examine what happens as the gold moves in and out of the control volume. So let's read our words to ourselves. Our conservation of mass, in this case, is the change in the extensive property of the system is d by dt of the integral of beta rho dV. And we'll use the Reynolds transport theorem to examine how that's going to progress in time. So consider our control volume shown. Well, we've considered that. I tried to do a big, exciting movie. Kind of like how to get people to watch the first commercial. The mass M is moving in a velocity field of V. So V has some velocity of X, Y, Z, and T, depending on where we are. So keep in mind this little yellow cube is moving, but we have really good stop action photography when you draw it yourself. So at time t, we have the situation where the mass is completely contained in the control volume. And you see we have the control volume labeled CV. Now a short time later, our gold block has moved. So some of it has actually left the control volume. And for the sake of simplicity, we're just going to simply have it translate from left to right. So now at time t plus delta t, our golden cube is shown here in the drawing, and our control volume is also shown in the drawing, and they're no longer coincide. Our gold cube is moved a little bit to the right, at least on the y-axis, and you see our control volume has two identifiable parts, part 1 and part 2. Part 2, does that have any gold cube in it? Okay, yes from the back. How about this side of it? Yes. I guess y'all say yes. Yeah, it has gold in it. And part 1 is now devoid of gold. So let's examine that in terms of the property of the system. So the change in capital B with respect to time of the system, if we went back to our gonculus stuff, it would be the limit as time goes to 0 of the amount of B at time t plus delta t minus the amount of B at time t divided by delta t. Since it's mass, it's all going to come out to 0. But if we examine the 3 zones and the system total mass, we can rename things kind of willy-nilly if we want. And let me get my handsome face over in the lower left-hand corner. That's a good place for handsome faces. Is B at time t is equal to the amount of B in the control volume at time t because everything is coincides. So this case B is mass. Times t plus delta t, system mass can't change because it's not allowed to, otherwise it would violate the principle of mass conservation. But we do know that the total mass in the system is contained in zones 2 and 3. There's none in zone 1. And so we can re-express B at time t plus delta t as the amount of B or the amount of mass in the control volume minus the volume that's vacated in zone 1, which it moved out of, plus the volume that it has occupied in zone 3, which it moved into. If we express that in terms of intensive properties, so now we'll apply the system to integral transformation. Our dB dt, if you will, is the limit as time goes to 0 of the integral over the control volume of beta rho dV at time t plus delta t, minus the integral over region 1, however big that is, beta rho dV at time t plus delta t, plus the integral over region 3, beta rho dV t plus delta t, minus the integral over the beta rho dV over the control volume of beta rho dV at time t divided by delta t. So that's just the definition of the derivative stretched out to include the location 1, part 1, part 2, and part 3 at the new time interval minus the whole control volume of the old time interval divided by the time interval. We can examine that a little further and observe the first term. The integral over the control volume beta rho dV at time t plus delta t minus the integral over the control volume of beta rho dV over delta t happens to be equal to the time rate change of the integral over the control volume of beta rho dV. That goes by the colloquial term of the volume integral. So when I say volume integral, I mean that thing. And it has a d by dt term in it. So if the volume physically doesn't change, what does that integral evaluate to? Good question, by the way. If the density is constant and the volume doesn't change, that interval will evaluate to 0. d by dt is something that doesn't change with respect to time. 0. Now, oftentimes that's not the case. Oftentimes the volume is changing or the densities are changing. But when both of them are not changing, that term vanishes. Unfortunately, it doesn't vanish reliably enough, so we got to at least write it once. The remaining two parts are the limit as time goes to 0 of the integral over part 3 at t plus dt minus the limit as time goes to 0 of the integral over part 1 t plus dt. And so we'll now use the divergence theorem to cope with the terms in part 1 and part 2 of space in the drawing. And I zoomed everything in because it will make some dice. So you remember the divergence theorem from engineering mathematics? It would have been, if you took it in a fall semester, you would have gotten around late October, early November. It'd still be warm and whatever room you were in, you'd have a hard time staying awake. So you just like here right now. But it's the theorem attributed to Mr. Gauss, which allows you to convert volume integrals into line integrals and line integrals into ordinary integrals. So you've seen this before. It may not have been explicitly called that, but in fluids, we're invoking the divergence theorem. And what it is going to allow us to do is the obvious. It's going to allow us to take that part 1 region, if you will. So that part 1 region, the gold left it. But since we're running time derivatives down to 0, there's a moment when the edge of the gold is coinciding with the left face of our cube. And so we can equate to the amount that was evacuated equal to whatever had to come into this place. That's all the divergence theorem is saying in simplified words. So if we do that, we apply Gauss's divergence theorem in this region 1, and we have the integral over region 1 of beta rho dv at t plus delta t is equal to the integral over the control surface. Notice the subtle change in subscripting there. Control volume, control surface, beta rho delta L dA1. And let's see where those came from. So if this cube didn't deform during its translation, and it moved delta L units this way to occupy zone 3, it had to vacate delta L units in zone 1. So the dimensions of zone 1 are delta L multiplied by dA1, whatever that face is. We'll quickly see that that's associated with the velocity at the left face. Similarly, we can play the same game with region 3. In this case, there's not a minus sign because region 3 is filling instead of vacating. And both those are Gauss's divergence theorem, and they produce what are called the flux integral. So in the limit, the region 3 term becomes the integral over the control surface of beta rho V2 dA2. And you can read that on your own there. And so the velocity at this face multiplied by that area is how much mass has to leave in some time limit. And that's where we get the velocity term and the area term. And the beta rho is just in this case, the mass flux. And similarly for the left region, region 1, we have minus beta rho V1 dA1. So let you all finish your collective yawning. Maybe you can yawn, it's okay. I know I'm bored. Don't worry about it. So what these integrals are expressing is how much mass is crossing the area. Let's go back to our front door there, where we'll make a street line. Each of you weighs about 175 pounds. For those of you that are nowhere near that, I apologize. For those of you that are a lot more than that, you're welcome. You start passing through that doorway. That doorway is an area. You'll pass at some velocity, roughly 2.5 to 3 miles an hour walking. So that mass times velocity is how fast we're vacating this room. So this room loses human mass at that rate. The hallway gains human mass at that rate, and it occurs right at that interface. So that's all the flux interval is trying to convey. And now we'll take a quick picture to look at the relationship of velocities and areas. So here's our same cube, but now we're looking at it just on the side. So location 1 is corresponding to this edge, and location 2, that edge. And if we were to draw explicit outward pointing area vectors, BA1 would point to the left, as drawn there. BA2 would point to the right, as drawn at station 2. We have a control surface, this case represented by a square. And if things are moving from left to right, at section 1, we have velocity 1 that's pointing into the square. Section 2, we have velocity 2 pointing out of the square. So that rho V VA is actually really V dot VA. It's the vector dot the area vector. If we were to evaluate that as section 1, the vector V dot VA, the area vector, would evaluate as minus V1 VA. The minus sign because the velocity term and the area term are pointing in opposite directions. They have opposite signs or the symbols. At section 2, V dot VA would equal V2 times VA2 positive value. That's because the velocity vector and the area vector are pointing in the same direction. Most of the time, we don't have to get this rigorous with it except for doing homeworks. It's usually obvious, but when weird stuff is happening or at strange angles, if you just evaluate the dot products correctly, it takes care of the sign. So now we'll collect everything back together and put it back in the fundamental equation. And basically what we have is Reynolds transport theorem. So in the case of mass, for conservation of mass, capital B, the system property, and this that's not an H, that's an M. But that was, during my whenever I wrote that, I must have been sloppy with the M. It's supposed to be a capital M. Our extensive property is mass, capital M. Our intensive property happens to be 1 in this case, which is mass over mass. And if we substitute that into this equation, which is essentially Reynolds transport theorem, we have that the change in mass with respect to time of a system is 0, because mass is neither created nor destroyed. It's simply transferred of all that stuff from the Discovery Channel, equals d by dt of the integral over the control volume of rho dv. So rho dv is simply the mass inside the control volume. So whatever the time rate of change of that is, plus any mass entering and leaving across the control surface. So volume integral plus flux integrals in the case of mass equals 0. And just an additional look at it, that d by dt integral over the control volume of rho dv is simply an expression of the rate of accumulation of mass in the control volume. In other contexts, we might think of it as the rate of change in storage. And then the flux integral, the rate of net mass inflow minus inflow rate plus outflow rate, or outflow minus inflow. Those things add together to 0, because that's what the system property is for mass. Or the other way to memorize it is inflow rate minus outflow rate equals the rate of change in storage, which probably would have been what I should have led with, but I had to do all that other rigmarole stuff. So that chapter that you paid 1/12 of whatever $125 is useful to you. So that's conservation of mass. Let's go ahead and do an application. And sorry about the title, but I was feeling frisky. So it turns out a grail is just a small bowl or a cup that you drink stuff from it. And in our case, it's got a hole in the bottom. So I got to make a pun at the expense of the upcoming Easter. I thought that, for me, that was fun. Y'all don't have to buy into that. But here's our problem. Let's suppose we're presented with this problem. We're going to apply conservation of mass. You could probably answer it by looking at it, but let's go ahead and do it too. lazy to just look at it and find the answer. I'll let someone else can find it, look at it, look at their stuff and copy it. But his notes aren't terribly good for copying right now. He's been doing a lot of doodling. So that's how I know it's cool. I'm not. I always ran it out from the phone. You got the doodles. Who else did I play? We'll get some more. I hope you don't find that offensive. You just kind of have some fun. So here's our problem statement. We have a stream of water flowing into an open tank. Speed of the incoming water is 7 meters per second. And the cross-sectional area, I guess of this square point, is 0.0025 meters squared. And somebody has good eyeballs to be able to tell that by just looking at it. The water is also going out of the tank through the hole at a discharge rate of 0.0033 meters per second. This is special water that has a density of 1,000 kilograms per meter cube. Means it has a specific weight of 9,800 meters per meter cube. Should have made it a little lighter so that all comes to that number. What's the rate at which water is being stored or removed from the tank? Okay, so this is in the continuity equation write-up. It seems like maybe that's the tool to write. But let's go ahead and apply our problem-solving technique. Do we have time? Oh yeah, we got plenty of time. I can have you all unconscious in 5 or 6 minutes tops, maybe less. I'm going to go connect to the server where everything's developed. So as we get done, I can say that we will have preserved this for prosperity. Ignore that. All right, so here's what it looks like when we're building things. Application of the Holy Grail. Obviously, we don't have the figure anymore. So what is our problem-solving protocol? Anybody remember? Okay, problem statement, and we'll stipulate that that exists already. What would our next step be? Don't do it all for him. Let someone else play. Sketch. Next step. Known. Okay, K-N-O-W-N. So in our case, what do we know? We know the velocity in is what? Okay, I'll go do it this way. 7 meters per second. The weird looking typing I'm doing has meaning because eventually we'll activate all that in the code cell. So we know our inlet velocity. What else do we know? We know our Q. I agree with you. We know Q out. Is it 0.003? We also know the area in. I have to go look that up. 2 zeros and a 25. We know the water density. Something else we know? What pulls you down to the center of the earth? Gravity. Spelled wrong on purpose. Do a 9.8 so that we're in the same units as everything. So it's in meters per second per second. Okay, you got any other useful information? Is to find change in storage. So what changes in storage could have possibly be figured out in numbers? It could be that what's going in equals what's coming out. In this case, the change in storage would be 0. It could be that what's going in is bigger than what's coming out. In this case, the change in storage would be positive. The tank could be filling up. It could be, it's like a bank account, that the amount going out far exceeds the amount coming in which case the water level is going to go down. So if we get anything other than those three, there's something wrong. So now let's go back to our picture. Draw it here on the chalk. I haven't formed chalk in years. I wonder what it's like. I would draw directly on that. We've already established that you can't use markers on this stuff. So here's our so how's that for a sketch? Like that? That's good enough. We can label Q. That's about all we have to work with, right? Rho. Okay, so we want to apply control volume analysis. What might be a logical first step? I'm intentionally slowing you down. Don't be the obvious, but what would make a lot of sense if you want to apply control volume analysis to analyze this problem? What's the control volume? That seems like a logical thing. Let's define the control volume. So what do you think it should be? Should it be all the water in the tank? Should it be the tank itself? Should it be the entire universe? She-Boat's universe. Don't listen to her. She's wrong now. Okay, I'll do the bottom part. I think the control volume certainly includes the tank bottom. We go up the sides for a while. And now we have to ask the question, if the water level in the tank goes up, where do you want the control volume to be? You want the control volume to move with the water, or you want it to stay put? Someone said stay put or move. How many for stay put? How many for moving control volume? Okay, you're both right, but the moving control volume is far easier to deal with. Because if it stays put, it's a piece of information that we don't know that we would need to know. We need to know the area of the tank if we're going to have water moving up and down the control surface. So let's go ahead and we're going to make our control volume for the gas volume. Here's my control volume, and I'm going to stipulate control volume and move the water surface. Okay, so I've done my sketch. I've defined my control volume. We've listed our names already. I'm not going to write those up again. It's actually in the drawing. So what's the next step? We actually have almost everything we need. The governing equations, which for this case is That one. Okay, so let's apply that one. We have d by dt integral of the control volume of rho dv plus the integral of the control surface of rho d dot dA equals 0. So now we have to convert that integral with stuff into something we can deal with. So at that point, as far as partial credit is concerned, we've got 25% of the problem done. Maybe 30 if I'm feeling better. So, like putting F equals NA for every problem we encounter, if that's not wrong, this may not be particularly useful. Where we've done everything that's not wrong, we now need to figure out how to express this term. And this is where this particular part I think is useful. This is just the time rate of change of the mass in the control volume. So in our case, we can simply state the depth as h. And so if this goes up, that surface has a velocity of dh dt multiplied by whatever area the tank has, and that is the change in volume. So we have 0 equals dh dt times the area of the tank. We don't need to know the area of the tank because it's going to move with it. So is that indeed a volume? Area has length squared, and h is a length, so that's length cubed. But it's supposed to be a mass, so what did I forget? It's a volume, not a mass. So how do we turn a volume into a mass? People on this side can see what I'm writing, so you all should be answering. What do you multiply? Wrong, but not bad. What do you multiply a volume by to get a mass? Yeah. Okay, so we've taken care of that. And it's not equal to 0 in this case because we have a moving control volume. Now we have to examine the flux intervals. What the flux intervals are telling us is what is the mass flow into and out of a control surface at the various locations. So let's do the easy one. We'll call this location 2, that location 1, because I have no originality in naming. So what's the mass flow leaving location 1? So outflow minus inflow plus the rate of change in storage equals 0. So we're now talking about an outflow. Magnitude of the outflow, 0.00. Actually, we'll do it in letters of the alphabet. Q. But that's a volumetric flow rate. What do we have to do to massify it? Multiplied by density. Very good. And I have to know that's flowing in, so I got to get the minus C. Velocity is going this way, and if we had an area that's pointing that way, so that's how we know it's a negative number. That's clear? So let's go ahead and create that negative number. I'm out of real estate. So we have minus VA 7. Actually, let's do it in letters of the alphabet. So we got minus V volume. Velocity times an area is going to be length over time times length squared. So we have length cubed over time. That's not a mass. How do we massify it? Say it. Multiply by density. Okay, so here is moving from here to here. You could have done this probably without that other stuff. But this is always a reminder of what we need to achieve in the analysis. Now at this point, we can mess with things around. Anything interesting about density in that expression? It's the same everywhere. Which means you could choose to multiply both sides of that equation by 1 over the density. Density found 0. And that would have the effect of if that go away, that go away, that go away. 1 over something times 0 is 0. Okay, cool. So we've gotten rid of the density. We'll never be able to get rid of the area of the tank. Let's move dH dt times area to the left side, and that gives us dA minus Q, which is probably what you would have come up with left your own devices without having all this fanciness in. What's next? It's about as far as we can get with letters of the alphabet. It's asking us, actually forget what the problem is. What is the rate at which water is being stored or removed from the tank? So at this point, we have to go ahead and put in the numbers. So B is 7, A is 0.0025, minus 0.003. If we did that arithmetic, we would have the rate of change. Let's go ahead and go back and just script it into our deal. Okay, so our change in storage, our formula is change in storage called dsdt equals what? In terms of the variables that we're creating up here. So this is us doing computational thinking, at least to the point of satisfying the dean's office expectation. So velocity times area. So that value, the miracle of cut and paste. Minus Q. Okay, so even though we pulled rho and G out of it, what we'll get if we evaluate that expression after we populate all the variables is we're going to get the volumetric change in our tank. If we want to know the mass change, what do? Multiply everything by rho. Okay, so let's go ahead and activate all that and see what happens. Area comes to life. Q comes, you know, when I should do these, I should actually see what the actual answer is. Oh, well, too late now. I think we got everything we need to know. I guess we should print the output. So we need to have a comment to label our output. Who wants to tell me what to say? No profanity, please. It's dull, so we might as well have fun. DSET. And assuming I have applied my computational thinking principles from Engineering 1330 correctly and haven't made any payments mistakes, I want to go ahead and execute that cell. It should print the storage accumulation is. Wait for it, whatever the DSDT is. So who already knows what it is? Oh man, what happened in the old days of people bringing out calculators and banging on them and doing calculator races? Well, let's see if we can figure out what it is without actually doing it. So we have 7 times 0.0025. So 7 is almost a 10. So that's going to move this decimal point over one place to the right. So we have 0.025 minus 0.003. So I think our value will be less than 0. It should be negative. Maybe not, because 7 is only almost 10. It's not actually 10. But we shouldn't get a number like 30, unless I've screwed something up big time. And so we get a slight positive number. So storage is actually slightly, that does not make sense to me at all. Oh, the arithmetic can't possibly be wrong. How could I make a mistake? And we would want to go check that to validate it. So our calculation seems to claim that storage is increasing. So anyone who's done it with their calculator already, can you confirm it is a positive number? Bueno. Did you get the same numbers I did? Oh, double blend. Okay, so that is continuity in its simplest fashion. We can make them that was almost where I wanted to end up. So here's a more typical example one might use to explore these ideas, but I think that one's a better one to start with. So in the 10 or 12 minutes we have left, let's just take a look at this. We're not going to do any arithmetic. We'll let the miracle of pseudo-Chegg do it for us. So let's suppose we have water entering a two-dimensional channel of constant cross-section, a width of h and a depth of d and uniform velocity. So it's entering here, everything's uniform. So all those little arrows are the same length. And as it goes through this channel and it takes a bend, when we look at the other end, at the outlet, the velocity on the inside of the turn is a little bit bigger than on the outside of the turn. So that might actually be realistic, although it's not going to follow these formulas at all exactly, but it's a good place to start. Channel makes a 90-degree bend that distorts the flow and produces a linear profile shown where U max is equal to twice the minimum value. We're asked to find U min. So when you see stuff like that, you're going, oh God, I'm going to have to use letters of the alphabet. There's no numbers to fall back on. Yeah, I'm afraid so. So our first step is problem state. Done. Second step, sketch. Done, it's up there, just like that. Next step is we probably want to establish what the control volume is. Here it's appearing as the second sketch, but often we just put it on the main sketch. So there's our control volume. It's that dashed L-shaped thing. Interestingly, attention is on the scale. So the features of the control volume on this drawing that are important are the control volume itself, the coordinate system, the y and x, and that is especially important when we start looking at those inner products between velocities and areas. The two sections are labeled 1 and 2, and we've also labeled the area vector. So we have dA of 1 is here, and it's pointing out. Is the U vector and the dA vector in the same direction? That'd be a no. So whatever that product is, it's going to be positive or negative. Negative. Good. Then we have the dA pointing up. It takes the velocity vector or the velocity field location. Now, are those velocities and area vector in the same direction? Yes. So when their inner product is computed, the sign is going to be further, right? Positive. Good. That's the important features of the control volume. So define the control volume, include a coordinate system. It's needed to write the integrals, and we're going to assume unit depth, and then we'll apply our friend continuity. And at this point, we just almost regurgitate continuity on command without thinking about it. d by dt integral of the control volume plus the integral of the control surface of rho v dot dA equals 0. In this case, our control volume, is it fixed in space? That'd be yes. So it's not moving. Is the density of everything constant? Probably. So the time rate of change mass inside that channel is 0. That's an example where that integral vanishes. So we're stipulating that here. It's 0 because the density is constant and the volume itself is not changing with time. In this case, we had the volume moving up and down. And then the integral over the control surface of rho v dot dA. And here the analyst has gone to the trouble to highlight the two sections. So here we are at section 1. We have velocity is equal to u in the I direction. The dA vector is minus dy I. And when you inner product those two, I dot J, excuse me, I dot I, is that defined? Yeah, that's a 1. So this will have a non-zero dot product. Same with J dot J. Here we have the area vector dx in the J direction and a velocity vector v of x in the J direction. So now we can break that integral apart into the 2 sections, the integral part 1 and part 2. I guess you could belabor it doing as it's done here, where we actually evaluate the integral. At section 1, we have rho u in the I direction minus dy I. We want to integrate that from 0 to h. How did I take 0 to h? So we're integrating that direction. We're integrating a distance to 0 to h, and we'll do the same up here. And so that's minus rho integral from 0 to h of u dy, which will be, it's going to be minus rho uy evaluated h and 0. So it's going to be minus rho u times h. Our second one, rho v at xj plus times dx at j, is rho integral from 0 to h v of x dx. We've changed the letter of the alphabet to v because we're now moving in the y direction. And we're given in the problem statement what the functional appearance of v is. It's 2 times u min minus u min over h times x. So that's expanding it out after the integration. And now we add the 2 integrals together, evaluate them, and we have minus rho u h plus rho 2u min h minus rho u min h squared over 2h equals 0. We observe that the rho is the same everywhere, so we'll just multiply both sides by 1 over rho, and we come up with u plus 2u min minus u min over 2 equals 0, and we can solve that for the minimum velocity u in terms of whatever the approach velocity is, which is unknown. So the important concepts here are: 1, avoid problems like this, like the plague, because if you have to do calculus, high likelihood of not getting it right. If you can't avoid it, try to find an answer somewhere else, and then work from both ends, and then hide that so that nobody knows that you didn't do it yourself. That's where your friends are. All those of you with check accounts, you can manage those diagrams. I'm not advocating check. I don't like it, but I'm also not a fool. I'm not liking it isn't going to make it go away. So if you have it, use it wisely. So the important concept in this case are to draw the control volume, draw the area vector. I suggest you write in the spectral components so you get the correct direction. Oftentimes you don't actually have to do those integrals the way we did them. You might be able to write the do integration by looking at it like we did here. Then we have to evaluate the v dot dA part in the integral, and use that to figure out the unit product. If you have the luxury that the control volume is fixed in time, then the density is constant, the volume integral will vanish. So then all you have to deal with is the flux integrals. How are we for time? 3:30 to 4:30. We got 6 minutes. I'll call it a day for that. You get to go 6 minutes early. Are there any questions? Well, thanks everyone for being a good sport, especially Purple, John, Sketcher. Just nickname Joe. And nicknames will last at least until you get out that door and we'll go back to the way we were.
Have a good weekend.
Y'all, yeah, have a good weekend, everybody. So brutal last semester. For this class, this is your second shot at it. Okay, good luck. You'll be fine. Well, she can be funny too, so it's. Just okay. You need to tell me to turn off the recording. Did we